Hello everyone, welcome back to the series of Mastering Digital Logic Design with Logisim. Today we will explore sequential circuits, the backbone of memory elements in digital system. We will learn about flip-flops, registers and counters, all of which are essential for designing complex systems. Let's jump right in. Let's start with sequential circuits. Sequential circuits are unique because they rely not only on current inputs but also on past states. This memory function allows them to be used in more complex systems such as counters, clocks, and memories. Sequential circuits are widely used in applications that require past state knowledge like timing, mechanism, or storing data. Let's look at the flip-flop. Flip-flop are basic building block of sequential circuits. These circuits can store a single bit of information, either 0 or 1, and retain that state until an input changes. There are mainly 4 types of flip-flops, which are SR flip-flop, D flip-flop, T flip-flop, and JK flip-flop. Let's start with SR flip-flop. The SR flip-flop, also known as set-reset flip-flop, has 2 inputs which are set and reset. Its outputs can be either 0 or 1 depending on the inputs. When the set input is high, the output Q becomes high. Conversely, when the reset input R is high, the output reset to low. If both are low, the output remains in its previous state. Let's take a look at the truth table for the SR flip-flop. When S and R both are low, the output remains unchanged. When S is 0 and R is 1, reset output to Q to 0, where its complement is 1. When S is 1, R is 0, set output Q to 1. When S and R both are 1, this state is typically considered undefined and should be avoided. Now let's jump into Logisim and build the SR flip-flop. Go to the memory component and drag the SR flip-flop into our canvas. Here you can see a caption which indicates a clock. So go to the wiring tab and drag the clock and connect it to the clock input of the flip-flop. Add 2 input pins which will be act as set and reset, and connect it to the inputs of the S and R flip-flop. Now let's add an output pin to observe the output of Q and Q bar. Now let's simulate the circuit by toggling the input and observing the output. Here you can see I can either manually toggle the clock by clicking on the clock on every second, or to keep the clock toggling continuously, go to the simulation tab on the top of the toolbar, and then you can select the ticks enable. This will keep your clock toggling continuously. You can also adjust the clock frequency by selecting the tick frequency in the simulation tab. By default, the clock frequency is set to 1 Hz. Now let's toggle the input set and see that either it set our output Q or not. As you can see, as soon as the rising edge occurs, the Q output of the SR flip-flop sets to 1. Now toggle it back to 0 and let's see what happens. As now the truth table shows that when both inputs are 0, the state of the Q and Q bar remains unchanged. Now let's toggle the input of R. This is going to reset our output Q. As you can see, the output changed to 0 and Q bar becomes 1. Now let's toggle both of the input and see what happens. Here you can see that nothing is happening because that state, the truth tables indicate that when both inputs are 1, the states are undefined. So let's toggle it back to 0, and you can see here again that nothing changes occur. If we toggle the set inputs back to 1, we can see the output turns to 1 where the Q bar becomes 0. Now you have seen the SR flip-flop and how does it behave on during different combinations. The SR flip-flop is widely used in basic memory storage application as it allows for the storage of a single bit of information. Next we will explore the D flip-flop, a fundamental building block in synchronous circuits. The D flip-flop or data flip-flop has one input D and is used to store a single bit of data. The D flip-flop captures the input data at the rising edge of a clock signal. The output Q takes on the value of D when the clock pulse occurs. Let's take a look at the truth table for the D flip-flop. When clock is 0, the output remains unchanged until the next clock edge occurs. When clock is 1, or you can say when the positive rising edges occur, and if D is 0, the output becomes 0. Again, when the clock is at the rising edge and D is 1, the Q becomes 1. Let's design the D flip-flop in Logisim. Go to the memory tab again, drag the D flip-flop into our canvas. Here you can see a cap sign which indicates a clock, so let's just connect the clock input to our flop, add an input pin to D, and add an output pins to Q and Q bar. Now let's simulate the circuit by toggling the D input and clock signal. Here you can see, as usually I have keep my clock signal on toggling continuously, so my clock keeps on toggling, and so let's just switch it off for now. Here you can see that my clock toggling has been disabled. So let's toggle it to the falling edge of the clock, and if I change the value of D, here you can see that nothing happening at the flop end. None of the outputs are getting changed. So let's make the D again to 0, and let's toggle the clock to the positive edge. As the input is 0, the output still remains 0. Now let's toggle the clock to the falling edge and make the D input 1, and let's toggle the clock to the positive edge. As you can see, as soon as the positive edge arises, the D input, which was 1, is forwarded to the output. Hence the Q becomes 1 and Q naught becomes 0. If we toggle the clock back to 0 to the rising edge, and if we also toggle input D to 0, and let's toggle the clock again, you can see the flop stores the new value of 0 and the output becomes 0 at Q and 1 at Q bar. Let's the clock keep toggling continuously, and so we can see the change at the runtime. Now let's have some toggling of D here. As soon as toggle the 1, it becomes 1. As soon as become the toggle D 0, the output becomes 0, or an inverse of it. Now you have seen how the D flip-flops captures the input on the clock rising edge. D flip-flops are widely used in registers, shift registers, and memory devices to ensure stability during clock cycles. Now it's your turn to explore. Dive into the T and JK flip-flops and implement them in Logisim to discover how they function in different digital circuits. Now that we have explored various types of flip-flops, let's dive into a crucial component in digital circuits, which are registers. A register is simply a group of flip-flops used to store multiple bits of data. It is a fundamental building block in memory system, processors, and data handling circuits. There are several types of register, including shift register, which move data in a specific direction, parallel register, where all bits are updated simultaneously, and counters, which increment or decrement stored value. Let us look into an example of a 4-bit register using 4D flip-flops, all connected in parallel. Each flip-flop stores 1 bit, so together they can store 4-bit binary value. Let's discuss how a register works. When the clock signal is applied, all the flip-flops in the register capture their respective inputs simultaneously and store them until the next clock pulse. Each D flip-flop in a register is responsible for holding 1 bit of multi-bit data. For instance, in a 4-bit register, the D flip-flop will hold 4 bits of data such as 1, 1, 0, 1. When a new clock pulse arrives, the data at the inputs of each flip-flop is updated and stored in the register. Now let's design a 4-bit register in Logisim. We will be using 4 D flip-flops to implement this and observe how the data is stored. Go to the memory section and drag 4 D flip-flops onto the canvas. This will represent the 4 bits of the register. Now let's connect the clock to single clock to each of the flip-flops, making it a common clock for every flip-flop here. Now add 4 input pins to represent the 4-bit input data. This represents D3, D2, D1, D0, connecting each input to the corresponding D input of the flip-flop. Now let's add 4 output pins to observe the output stored value. Connect the Q output of each flip-flop to the respective output pins, which will make it as Q3, Q2, Q1 and Q0. Now let us simulate the circuit. We will going to apply different binary inputs, for example 1101 or 1010 to the D input pins and toggle the clock signal to see the register stored the new values or not. Before that, let's disable the ticks enable of the clock. Go to the simulation tab. As you can see, the clock is at the falling edge at the moment, and if we toggle it back to the rising edge, nothing happens because all of the inputs are 0. Now let's toggle it back to the falling edge of the clock and place a binary combination of 1101. Now let's toggle the clock to the positive edge of the clock, and here you can see that all the updated values have been stored in the registers. The output shows the same exact pattern which we have provided as a input. Now let's change it back to the falling edge and change the input to 1010. Here you can see that as a falling edge, nothing has happened, none of the output gets changed. Let's toggle the clock back to the rising edge, and here you can see the output is updated with our new pattern, which is 1010. Now let's enable the ticks enable to keep the clock toggling continuously, so we can change the input pattern at a runtime and see the changes occurring. Okay, I'm changing the pattern to 110. Here you can see the output has been updated. Okay, let's make it all 10. So you can see here the output again gets updated 0, 0 and 0. That's how a 4-bit register works. We have seen how flip-flops work together to store multiple bits of data, and we have successfully designed and simulated a 4-bit register in Logisim. Now we will explore counters, which are essential digital circuits used to keep track of the number of clock pulses received. We will be discussing two main types of counters, the asynchronous counter, often known as a ripple counter, and the synchronous counter. Let's look at the asynchronous counter. In this type of counter, each flip-flop is triggered by the output of the previous flip-flop. This creates a ripple effect as the counting progresses, leading to some delay in the output changes. In a 4-bit asynchronous counter, the first flip-flop is triggered by the clock pulse. When it toggles, it generates an output that serves as a clock input for the next flip-flop. This continues through all flip-flops, creating a ripple effect as the count increases. For example, when the first flip-flop toggles from 0 to 1, it triggers the second flip-flop, which then toggles. This process continues down the line. Now let's simulate a 4-bit ripple counter in Logisim using D flip-flop. Go to memory section and drag 4 flip-flops onto the canvas. These will form for our asynchronous counter. Connect the clock input to the first D flip-flop directly to the clock signal. For each subsequent D flip-flop, connect the clock input to the inverted output, which is Q0 of the previous flip-flop. So the Q0 of the flip-flop 1 will become the clock input for the second flip-flop. The Q0 of the second flip-flop will become the clock input for the third flip-flop, and the Q0 output of the third flip-flop will become the clock input for the fourth flip-flop. The input D of the flip-flop will be connected to its own flop output of Q bar. So we are going to connect the Q prime to its own input. Same it goes for the second flop, and same will be go for the third, and same will be happen for the fourth. Now let's add 4 output pins to observe the Q outputs of the flip-flops. Connect each output from Q3, Q2, Q1 and Q0 to the respective output pins. Now let's start the simulation and observe the counting sequence. Each clock pulse will cause the output to change, demonstrating the asynchronous counting behavior. So first let's just stop the text toggling. As you can see, the counters have already been updated. So go to the simulate tab and reset the simulation. This will going to reset your whole simulation back to the reset values. Here you can see that all of the outputs are at 0. So now let's toggle the clock one by one to see is the really we have developed a 4-bit asynchronous counter or not. Here you can see the clock is at the falling edge of the clock. So as soon as we toggle it, you can see the output of the first flip-flop becomes 1. So you can count it like 0, 0, 0, 1. So it is your Q3, Q2, Q1 and Q0. So my counter started from incrementing from the count of 1. Let's toggle it back to the falling edge and let's toggle it back to the rising edge. Here you can see the output of the first flop becomes 0 and the output of the second flop becomes 1. This makes the count of 0010, which is 2 in decimal. Let's toggle the clock again. Here you can see that first and second both flops gets 1, which makes it a count of 0011, which is 3 in decimal. Now let's keep the clock toggling so we can see the actual working of our counter. So you can see that it changes to 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and all the way back to the 0, as we have designed a 4-bit counter so it can count from 0 till the maximum value of 15. So this is how a simple asynchronous counter works. Now that wraps up our exploration of the 4-bit asynchronous counter using the flip-flops. In this design, we have observed how the output of each flip-flop is dependent on the inverted output of the previous one, creating a ripple effect as the counter increments. This setup illustrates the fundamental concept of asynchronous counting, where each flip-flop triggers the next one based on its output. Now it's your turn. I encourage you to take what you have learned here and try designing a synchronous counter on your own. Unlike the ripple counter we just built, a synchronous counter will have all flip-flops triggered by the same clock pulse, allowing for faster operation and eliminating the ripple effect. Experiment with different configurations and see how they affect the counter's performance. This will deepen your understanding of sequential circuits and how they function in digital logic design. And that's a wrap up for our session on sequential circuits. Today we have explored several key components: flip-flops, registers, and counters. Each of these elements play a crucial role in memory storage and decision making within digital circuits. I encourage you to practice these designs in Logisim and experiment with creating your own circuits. The more you think, the deeper your understanding will become. In our next video, we will dive into the fascinating world of the arithmetic logic unit ALU, where we will learn how to perform arithmetic and logical operations in digital systems. If you have enjoyed today's sessions, don't forget to like, subscribe, and share with your fellow learners. Your support helps us continue creating valuable content. Thank you for joining me today, and I look forward to seeing you next time.